Hey there, chemistry team. Welcome to video number 10 on acids and bases. We're going to be looking at polyprotic acids and bases today. We've been only looking at monoprotic acids that only give off one acidic hydrogen, or bases that can only pick up one. We haven't looked at the fact that maybe something can give off two, like H2SO4 or H2C2O4, maybe even three H3PO4. That's why they're called polyprotic acids. And the same thing with bases. Sometimes bases, if they have a -2 charge, can pick up two H pluses, or if it's an amine that has two nitrogens with lone pairs, it can pick up two. You'll see a few on your KB table. But before I get started, wanted to introduce to you Griffin, our beautiful bearded dragon. Rawr. So prehistoric looking, eh, Griffin? Say hello, you beautiful creature, you. Yay, Griffin! I've gotten lots of requests to see my strange pets in my house. All right, go eat your crickets, Griffin. Say goodbye, big guy. All right, here you go, Goose. All right, out you guys. Close the door behind you. Close the door behind you. Thank you. Pets are awesome. Okay, anyway, let's take a look at some generic polyprotic acid. These can be exceedingly difficult if you just beat your head against the wall and try to attack it. So we're going to make quite a few assumptions. Us chemists like to make assumptions, right? So we are going to make several assumptions to try to reduce the polyprotic acid problem into a monoprotic acid problem. Or if it's a diprotic base, right, it can pick up two H pluses. We're going to try to reduce it into like a monoprotic base where it only picks up one. And then we can just do what we've been taught before with ice tables and all that fun stuff. So let's do a generic polyprotic acids. This one would be diprotic with the two hydrogens. I'm not going to give you guys triprotic acids and bases on quizzes or exams. They're a little more extensive, but you could do it. I know in the textbook it talks about how to follow along for like phosphoric acid, H3PO4. So you can read through that, but I'm not going to give you anything more complicated than a diprotic acid or base. And I'm only going to do the acid part. The base follows the exact same thing. All you got to do is put a KB where I put a KA, and it would work exactly the same. So let's say we got some generic diprotic acid here. It's got two ionizable H's, right? You might have something with 6 hydrogen atoms, but they have to be ionizable, usually connected to an oxygen atom, not to a carbon atom. That's why we like to separate them as general chemists and put the acidic hydrogens out front. So this can donate an H plus to water, right? Forming our hydronium ion in our conjugate base, even though in this situation our conjugate base has a hydrogen which could also potentially ionize. So this comes down. Let's take this species here, and that can now come down in step 2 to further ionize. Let's write that out. So let's take the HA minus, whatever A is, doesn't matter. That can also donate a proton to water, just like it did in the first step. So this could go, hey, I got another one to give. Yeah. Right? Happens in multiple steps. And the reason we do this is because it's different in each step. We're going to find it gets harder and harder to lose that H plus or give that H plus away. I'm going to talk about why. Hopefully you can see it before I tell you. So in this case, we'll get the A2 minus, right, the conjugate base of this, plus another hydronium ion. Oh no, this is going to be a problem. We're going to have, if we're trying to get the pH of these solutions, we're going to have 3 sources of hydronium ions. What do? Make assumptions. Let's call this K, because these both have Ka values, right? So let's write our Kas here. So this has a Ka value. This has a Ka value. So we just can't call it Ka anymore. We're going to call it Ka for step 1 and Ka for step 2. And if you look on a Ka table, you'll see that, for example, right? You can see the ones like arsenic acid, right, has multiple K values. You can see they change as they go down. They're not the same. So you can see the polyprotic acids like citric acid, hydroselenic acid, hydrotelluric acid. They have the multiple steps with different Ka values, right? Quite dramatically different. And if you look at, for example, pyrophosphoric acid, whatever the heck that is, right? Goes from 10 to minus 2 to 10 to minus 3 to 10 to minus 7. As we lose hydrogens, each step becomes increasingly more difficult, and we're going to use that factor as a way to simplify the mathematics when we do this. The main point I want to take away from this is the Ka2 value is going to be way lower than the Ka1. This will be less acidic than this because, look here. Here we're taking that H plus from a neutral species and bringing that over to water. Here we're taking that H plus from an anion over to water. It's going to be, see the positive and minus? It's going to be a lot harder to rip that H plus away from an anion than it is for that. That makes this a very, very weak acid. All right, so here we're removing H plus from an anion. That's not favorable. This is going to be very, very important when we make, because without this, we can't make the assumption and the mathematics becomes really hairy. Therefore, Ka2 will be less than Ka1. And if it was a triprotic acid, if there was a third step, the Ka3 would be way less than Ka2. This is going to allow us to make an assumption in a second here. We can, if, you ready? If Ka1 is greater than 1,000 times Ka2, or if we're doing a base, Kb1 is greater than 1,000 times Kb2, right? So if this is 1,000 times higher than that, we can make the assumption that the second ionization step is pretty irrelevant, right? Because we're looking at, hey, if I want to get the pH of this, how much hydronium am I producing here? And I'm also getting some hydronium from here. Well, if almost all of it comes from this first step, because this is such a low Ka value, the amount that you produce from here is so insignificant versus how much you got in step one, we could just ignore. It's like, like taking two numbers, 1,000 plus 0.001 is still kind of 1,000. Just those aren't the numbers we're going to get, but you get the idea. It's effectively zero compared to that. So we can do a little test here. Take 1,000 times the Ka2 value, right? And if your Ka1 is still bigger than that, we can make a really important simplifying assumption that all the H3O plus comes from step one. Right? If this is true, then we're going to assume the hydronium ion concentration from the second step is negligible. I don't know how to spell negligible. Negligible. So small, we can ignore it. Versus step one. I cannot emphasize how important this assumption is. This allows us to ignore the second step and only focus on the first step, which is just like any monoprotic acid or base problem we have dealt with in this chapter, and life goes on as normal. Of course, I'm not going to give you one where that doesn't work on a quiz or exam, because I'm not going to teach you how to do it if that doesn't work. But you have to do it. You have to prove to me that this is true, so you can say, hey, the hydronium ion from step two we can ignore. So what I'm going to do is I'm going to pause this, and I'm going to put up a new board, and I'm going to get you really thinking about, there's actually 3 sources of hydronium ion. We're going to write those up there, talk about the simplifying assumption so we can reduce it down to one source. Be right back, my friends! Okay, guys, busy board. And this is something we're never going to write again. All right, I'm only going to do this one time, but this will be true for every single polyprotic acid or base problem you do. You have to think about these in the background, and I will be assigning points for these assumptions. 3 sources. If we have a diprotic acid, if you have a triprotic acid, we'd have one more source of H3O+. Every ionizable step would be a source of H3O+. First one, water autoionization. Remember, these are occurring in solution, so we've got water lurking in the background there, reacting with itself with the Kw, forming some hydronium ion at 1 times 10 minus 7 molar. So it's tiny, tiny. And in the presence of the acid, that gets reduced even more. So we can just ignore that the any hydronium ion from water autoionization is so small it's negligible. We can just ignore it. Yes, we've been doing that for every single problem, and we assume it so often we forget that we're even assuming it. So we forget to write that down, and that's okay. I'm not going to be assigning points for that. That's just an assumed thing. Well, we're going to have the first ionization step for our diprotic acids. That's going to give us, if you look on that last board, that first, it's going to react with water, donate its H plus to form HA minus and H3O plus. That's a source of hydronium. That is by far the dominant source. And what we're going to be assuming is that's such a dominant source compared to the other two that we only have to worry about that source. The other two, we can just ignore them. And that really simplifies the mathematics. If it doesn't, the book talks about ways to do it if that's not correct with some fancy mathematic gymnastics. And that's okay, but you don't have to learn that for this particular level. If you move on to higher levels, then you can work on those problems. All right, the third source of hydronium ion will be from the second ionization step, right? Because you form the HA minus in step 1, that comes down in step 2, can also ionize. But that has a very low Ka value, right? The Ka2, because you're trying to rip an H plus off of an anion. That's not very favorable. And it's a really, really low concentration. I didn't mention that before, because that's coming from the ionization in the first step, which is a weak acid, right? This doesn't work for strong acids. If it's if it's a weak acid, if H2A is a weak acid, that first ionization step, you're hardly going to get any of the HA minus and H3O plus anyway. And then you're taking that low concentration of HA minus with a very low Ka value and trying to ionize that again. The amount of hydronium ion you're going to produce is pathetically small. And as long as Ka1 is greater than 1,000 times Ka2, we can ignore step 3. Bam! We can ignore step 1 and only follow step 2. It's going to make life really, really nice. So let me set up kind of a generic way of looking at this using some, generic acid H2A, and then we'll do a specific acid on a different problem. These are fairly extensive problems, but once you know how to do it, once you know the tricks, you can whiz right through these. All right, gang. So I rewrote the first and second ionization steps. You can if you want to. You don't have to. But I wanted to do that so you can see the equilibrium expressions for step 1 and step 2. All right. So the Ka1 will just be the products, the HA minus times the hydronium ion raised to the power of 1 over the reactants, the original diprotic acid. We don't include the water, right? And for the second ionization step, which we're assuming is negligible, we're not assuming it doesn't happen. It does happen. It's just the amount of hydronium you get is so tiny. How tiny is it? It's so tiny. Compared to that, we can ignore it, right? We're not assuming it's not happening. We're just assuming it's so small we can ignore the contribution of the hydronium ion from step 2. But if I do the equilibrium expression for that, it would be the concentration of the A2 minus and the hydronium ions raised to the power of 1, because of the stoichiometric coefficients of 1, over the HA minus, and we're assuming that's very, very small. Right? Let me show you a neat little trick here. pH should be pretty easy to do because we're assuming the hydronium ion from that is all from, is the dominant source. But remember, we have to do Ka1. If Ka1 is greater than 1,000 times Ka2, we can assume this is negligible, right? The second step. But what does that mean? What does that mean? I'm going to show you a neat little trick. And the reason I'm going to show you this trick is, what if I ask you the concentrations of all equilibrium species? Oh no. Because remember, I could ask you percent ionization. I could ask you pH. I could ask you the concentrations of all species at equilibrium. Those are the 3 main things we solve for. pH would be pretty easy. We'll just set up an ice table for this, solve for H0 plus X, right? Make your assumption that X is small, just like we've been doing for type 3 equilibrium problems. Boom, we got our H0 plus. Take the negative log of that and you've got the pH. And we're going to do that in a problem in the next video. But what if I ask you, what are the concentrations of all species at equilibrium? Which would be, what's the concentration of this? Which will be the initial minus how much ionizes. You look on the equilibrium table for that. How much of this forms, which would be X. how much of this forms, which would be X. But if this comes down, then that's reducing. See what I'm saying? Then it wouldn't be X, it'd be a little bit minus X. But if our assumption is valid, if we assume that this second ionization step is so small, we can assume the concentration of HA doesn't drop any significant amount in the second step, so it's still the original concentration it forms up in step 1. So if this is true, then the concentration of the HA minus you form would be equal to the concentration of the hydronium ion, because we're ignoring that second step, right? Second step is ignored. Therefore, we can calculate the concentration of HA minus. It's just the concentration of H2O plus. That makes life nice and easy, right? But what about this species here? Remember, this step is happening. It's just we're just assuming it's small. So how are we supposed to get the A2 minus concentration? Oh no! A lot of students on exams just skip that step because they forget this nice little, it's not a trick, but it just works out mathematically. You could set up an ice table for the second step and plug in the values here and just solve for, because you know Ka2, right? We know HA minus, we know H2O plus, right? We're just solving for A2 minus, but you can skip the entire ice table for the second step, because what we can do, you ready? If the HA minus is equal to the H3O plus in step 1, because this assumption was valid, right? This assumption is valid. Isn't this equal to that? Isn't that true, right? So at equilibrium, watch this. Oh, this is so slick. You're just going to kick yourself how simple this is when you see it. At equilibrium, HA minus equals H3O plus. Can you see where we're going? Can you see where we're going? So Ka2 will be equal to A2 minus, that's an ugly looking 2 minus, times the hydronium. Can you see it? Can you see it coming? Over HA minus. But these are equal to each other. So those are going to be the same value, and they go adios, man. They're gone. They went trick-or-treating. Their history. That would mean those drop out, and that's the only thing you have left. Therefore, if I say what's the concentration of all species at equilibrium for a diprotic acid or base, if it's a base, just put a Kb2 there. That's it. It's exactly the same process. Then the concentration of that little tiny species that it just dribbles out of there, there's hardly any. I'm still here, don't forget me. It's still there, but it's so small everybody just ignores them. Right? Then the concentration of that species will just be equal to the value of the Ka2 on your Ka table. Boom! If you know that, if you understand that because you did your homework and the practice tests and worksheets and labs and all that, you're on the test, you look at that and go, boom, it takes you 2 seconds. It's so simple, it's so cool. Let's do another video because it's going to be a little bit long, and we will do an entire problem for a specific diprotic acid. Make sure you look at the practice test because I got some for diprotic bases as well, and you can read through the homework. Homework does triprotic, not the homework, the textbook does triprotic acids if you're interested. So we'll kill this video and move on to the next one where we'll do a type of problem you'll see, hint with a capital H, what you'll see on the next exam.